We'll start. I'm sorry. We'll start within a minute or so. So maybe we'll start today's class. I guess you guys can hear me. Yes. So, welcome to today's lecture, which is problem solving session of this course titled as Sensor Technologies, Physics, Fabrication, and Circuits. And this is the week 6 of this course. And I am Shomat Bhattacharjee. I am pursuing my PhD from IIT Jodhpur. To just a second. So, to know more about me, this is the usual thing I have to do. So, my name is Shomnath Bhattacharya. I am pursuing PhD from the Department of Electrical Engineering, IIT Jodhpur. My research interest lies in the field of flexible field effect transistors and organic transistors for neuromorphic computing. My educational background is like I have completed my master's in electronics. I have completed my bachelor's in physics. And to know more about me, you can find out in the details. I have given the link and also my LinkedIn profile. I usually take class on every Monday from 7 to 9. And like I'll have some extra class, and I guess you guys can suggest which day is fine for you guys also. And so this is the 8 factors of this course, out of which we have started with this basics of sensors, introduction, and those things. Then afterwards we have moved to the basics of sensors, the parameters of the sensors, the key parameters which we use to characterize the sensor. Is it good for your sensing application or not, or those things. Apart from this, we have learned the physics of sensors, the capacitive and thermal sensors, resistive sensors, impediometric sensors, chemical sensors, and optical and magnetic based sensors. In this class, we'll learn about the fabrication and characterization. Uh, we'll start the fabrication and characterization part, where we'll learn about the deposition techniques, and then we'll move towards the patterning afterwards. So we'll learn a bit about the patterning in this class, and afterwards we'll learn more in depth about these things. Yeah. So at first we'll just learn about what is a clean room because each and every fabrication requires a clean room. The basic thing about clean room is that you can think of if the room is not clean. Let's say there are like these standards are there. So out of those, like we can see that based on the ISO standards, there are ISO 1 to ISO 9. So these are the clean room standards. So apart from these things, so what happens that let's take an example maybe. So in case of ISO 1, that is the extremely clean room, right? What happens? There is 10 particles of zero point 0.1 micron. So zero point 0.1 micron, 10 particles are there. So you can say that it is very unlikely that that 10 particles will be on top of your device. But let's say that if your device structure is like this, just a straight line, right? This is your device structure, and this thickness is 20 microns, let's say 20 or 30, maybe 30 micron, let's say it's 30 micron. So what will happen if the channel is like this? What will happen if there is contaminants in the room? So if there is only like let's say three contaminants back to back, so it will cover up the whole device channel, and no electricity or anything will flow through this, right? So what we need that we need a very clean room in which this is a very unlikely case where only three particles will be on top of each other. But let's say there's a case like this, right? So what will happen? There will be a issue like this. Okay. So to avoid this kind of a contaminant based issues, we move towards a cleaner room where we have the setup, and if we are fabricating the devices there won't be any kind of a contaminants, or it is very unlikely there will be contaminants on top of that device. So based on your devices, based on your sensors, the standards of the clean room required is more and more. So the best classified clean room is the ISO 1. This is the ISO 1. There is only 10.1 micron particles there. There is ISO 2. And the most common one is the class 1 clean room. That is the ISO 3 clean room, right? And this is class, in like general air. So this one is the like a cleaner room, just a cleaner room, right? But you can see there are like huge particles there. Like if the particle size is zero point 0.5 micron, there is this many amounts of particle. So if you are like working with, let's say 30 micron of this. So sorry, just wait a second. Maybe I'll just swipe it upwards. Yes. So even let's say there are only like this amount of things there, 30 microns, what will happen that only zero point 0.5 microns, but still like there will be so many particles, and obviously there will be contaminants here. So we need a more cleaner room, and to make the room clean it's a very costly process. Okay, so it requires a huge amount of money to make the clean room and also to maintain the clean room as well. So the major problem is the maintenance of the clean room. It requires a huge amount of money because anyways if there is let's say this is a clean room, so what you need to do every time is that you need a constant flow of air inside the clean room and constant flow of the air outside the clean room. You can't use any kind of a cloths that have lints. You can't use any kind of a erasers or those things. You can't use like you have to use specific grade of pens and not pencils. You need specific grades of pen to use in that. Even the papers should be of specific grade to use in a like specific clean room on those things. So let's learn about more about this clean room thing. So this is a basic user protocol where if we need to enter a clean room, what we need to do. At first, the major thing, the major contaminant of a room is nothing but a human body, right? So the problem with human body is that a person can have dandruff, a person can have cloths which will lint will follow from this cloth or those things. So at first we need a cap which will cover our hair, and any kinds of contaminants from our hair will be blocked. Then next one is shoe caps, or even particularly a different kind of a shoe. So what happens if you have shoes that will cover your if you have let's say sneakers or something of thing in case of lower grades of clean rooms, what you can do, you can use just a basic shoe cover and you can cover your shoes, and the dust and those things will be covered up. But in case of higher grades of clean room, what you will do that you will have a specific kind of a shoe which you will use inside that room also. Then you will have clean room gloves. Normally, these are kind of a sterile gloves. Maybe you have seen like a purple kind of a gloves or blue kind of a gloves. So those are the sterile gloves or the clean room gloves. Then you'll need a mask. So and in most of the cases, having a beard or those kind of a things are in outside countries are kind of a restricted. So you can't have a beard if you want to work in a clean room and those things. But in our in our country, we used to wear a mask and those things. Then hood is necessary in many cases, but not always. But you will need a total, this is called a bunny suit. So what happens that it is a jumper suit, so you will have only a single suit which will cover from your legs to directly to your head. So it will be a single suit, most of the cases like you have seen in the videos maybe. So it's in white colors or blue colors, and so this is a total body suit. That's why it will protect the equipments and all the even all the devices you have prepared or fabricated from the contamination coming from your body itself. Okay. So apart from them, there can maybe some eye kind of a eye protection where it requires a laser kind of a thing or those things. So you need eye protection. Other than that, you normally have a tachymat, which this is a very peculiar way. So what happens that if you just want to enter a clean room, right? So there's a basic room, which is the changing room. At first, you need to remove all the extra clothing you have, like jackets or those things. Then you have to put on this kind of a bunny suit at first, and then you have to change your shoes and change your gloves and those kind of a things. And after that, even after that, so if you are totally clearing that, there may be a jet spray which will send some antifungal things and to decontaminate your body and those things. And after that, there will be a tachymat which will take all the dust particles, those things away from the basic chamber as well, because in the basic chamber you would require a certain level of cleanliness, because as you can see, this, if this is the clean room, this is the changing room. Okay. So you need to also maintain this changing room cleanliness. So in any ways, you have to maintain cleanliness in this room, and this is the ultimate room. But still, you have to maintain cleanliness in the changing room as well. And while you are coming out of this room, there is only single way, because having so many different ways to enter your room and getting out of your room is hectic and also very costly. Along with that, the cleanliness will be tampered, so that's why we need a single entry point and single exit point as well. So from the same changing room, you have to come out of the room, and you have to just what do I say, you have to first remove your gloves. You have to just follow the previous steps, but in backward order. First you will have to remove your gloves, then you have to remove your eye protection, then you have to remove your boot gloves, and then the overall suit, then your the cap, and then the shoe covers and those things. So it will be in backwards. So to maintain this, like it's a hugely matter, and so in most of the places, like even having a class 100 or class 1001 is fine. Let's open this page maybe. Yeah. So having a class, sorry, even having a class 1000 and class 100 is also perfectly fine, and like most of the clean rooms are in these classes, because like having these classes is like it has some disadvantages obviously, but getting this kind of a class like class 10 or class 1, like it is a hugely costly matter. So what happens that most of the labs uses this this 100 to 1000 range. Yeah, sorry. So we'll move towards this kind of a deposition technique. So broadly, we can classify this deposition techniques in two parts. That is the physical vapor deposition or PVD, and another one is the CVD. So in PVD, what happens? There's a physical vapor of the material you want to deposit, and it is directly deposited on top of the substrate. Let's say this is the material here, and by some means it can be heat, it can be like bombardment or some kind of a thing. What happens that these things travel directly to the surface you want to coat, or the substrate on top of which you want to coat the material. So this is physical vapor deposition, which is physically, like in this cases, the material is physically traveling to your substrate and getting deposited there, right? In case of chemical vapor deposition, what happens? It happens in a chemical way. So what happens? By a flow, by a specific flow, it can be different kinds of flow. It can be like argon or those kind of a things, or even it can be of some kind of a different chemicals or oxygen or nitrogen, this kind of a thing. What will happen? There will be a physical flow of a vapor, but there will be chemical reactions happening. There is no bombardment or no directly hitting the target or those things. What happens? There will be a chemical deposition, and without any stress, there will be deposition, and the byproducts, and also the byproducts, and also the remaining gases and remaining things comes out of a separate way. So there are majorly two types of deposition techniques, that is a PVD and a CVD. Apart from this, there are several techniques like oxidation, where what happens that we heat the substrate, and in a specific condition with like let's say a specific pressure or a specific heat, the sample let's say silicon will oxidize into silicon dioxide. So in if this is a silicon, let's say this is a silicon bar, if we heat it like in a oxygen rich environment, what will happen? The resulting thing will be like this. So it will increase in the volume, but here it will be divided in 45% and 55%. So the silicon will get oxidized. Here this part, let's say this is silicon dioxide, and this part, this, let's say this is the second part, darker one is the silicon. So it will get divided into two parts. So it will be physically changed, but we can say it is a physical vapor deposition, kind of a different thing, because like it's taking the material from it like within itself. So this is a different kind of a thing. So this is called as thermal oxidation. So in case of silicon to silicon dioxide or those kind of a things, like usually we do it for the wafers and these things. Sorry, yeah. So wafers and these things. Yeah. So the basic difference between these things is like you can see like with PVD and CVD, the basic difference is the deposition rate. So if you want a like higher rate of deposition and those things, PVD is a perfect way. Always like prefer PVD if you want to like deposit within a few hours or so. So this is the perfect way. Other than that, the conformability is very low in PVD. So what happens here? It is very low. So conformability is a let's say a specification where what happens if you have a block of this, you want to deposit on top of this. What will happen if you have let's say a green something? So conformability is the deposited thing will be conform to the surface, top surface of this thing, right? So there can be like left spaces here or those kind of a thing. There won't be spaces. So in case of PVD, in physical vapor deposition, as it's very fast and those things, what happens that in case of PVD, there is like the spaces left. There can be errors in the like conformation. If the structure is like this, let's say the structure is like a square, the structure may be like this afterwards. So you can see that there in some spaces that the deposition is higher. In some places, the deposition is a bit lower. And in most of the cases this is done for like let's say gold, silver, this kind of a things like metal things. And in case of like CVD, we do it for oxides like let's say mm, aluminum dioxide or hafnium dioxide, this kind of a things, we do it for this kind of a things. And usually in case of PVD we need a lower temperature, but in case of CVD we need a much higher temperature actually. And then that it is direct way, you can see that is it is inside its line of sight, so it is a direct thing, you can see that. Okay, but in CVD there can be like here you can see that there is no line of sight, right? Even if it's there can be like deposition here as well. So in case of CVD, you will give a more confirmed structure where everywhere there will be like let's say you need a 10 nanometer deposition, and everywhere there will be a deposition of 10 nanometer only. Apart from this, there is another technique that is called the ALD. ALD is also another type of CVD, although we can't classify it directly as an like CVD. So in case of ALD or atomic layer deposition, there's a deposition that is that happens layer by layer or atom by atom. Let's say each layer is of one atom, so there will be a deposition of one layer and there will be deposition of another layer. So you can make composites of each like different materials as well. If this is material A, let's say this is material A and there is material B, there can be material of A. So in case of PVD, let's say you want to make this kind of a structure from PVD, what will happen if you have two different targets? So like let's say a structure is like this, where you have two things, right? You heat both the things, but there won't be because of like changed in their like melting temperature as well. So what will happen? There won't be equal deposition of both the materials. So it will make a composite. Obviously, there won't be this layer by layer structure, but there won't be equal deposition as well. Let's say if you have, let's say, copper and gold. So what will happen that it may happen that the copper is totally deposited, and but you still have some gold left in in this boat, the container which holds the material, right? So we'll discuss more in depth of this like in this techniques as well. So let's move into the thermal deposition technique, which is the most commonly used PVD technique. It is a physical vapor deposition technique. Just wait a second. So in case of a thermal vapor deposition technique, what happens that in the first step is this is called a boat. This structure looks like this from the top view. This looks like a boat. So there's like a valley inside this one as well. So we put the material inside of this. We put the material inside of this, and what happens that this boat is heated, right? So this boat is heated. So the at first the material is heated, or material is heated, and by heating the material, yeah. So by heating the material up to its melting point, so the material changes its state from solid to vapor, or let's say gaseous state. Okay, so it gets melted in a very low pressure. In general, it's used as like 10 to the minus 6 torr. So in this kind of a low pressure, the material is heated. What happens that the material starts shooting then. So because of this heat, the materials is directed towards the substrate or the like surface you want to deposit the material on. It's directed towards the substrate, which is hold it in a like a higher position. So just a second. Yeah. So the substrate is just put here. So there's a physical deposition of the material on top of this surface. Okay. So if the surface is like this, the material is flown to this, and through this direct line of sight, there will be materials deposited on top of this surface. Okay. So like there can be errors as well, because if you want a specific kind of a design or those kind of things, what will do, you will use a shadow mask. Which is a shadow mask? Shadow mask is a like a stencil, kind of a stencil, which is made out of a metal. You will have some kind of a design made on top of it. So there will be like spaces. So within the shadow mask, the materials will go through this shadow mask, and it will create this kind of a structure, let's say, on top of the substrate itself. So with this kind of a structure, there will be some problems. There can be shadow effect. If the shadow mask is a bit thicker, what will happen? There will be a kind of a shadow effect. So there will be a smudge kind of a issue here. There will be a kind of a smudge kind of a issue here. So apart from this, what happens that if we are using two boards at the same time, so even if we are using like two boards at the same time, there won't be like, as I have said, like if you are using copper and gold at the same time, what will happen? There will be a composite of these materials, but as like both the materials won't have the same deposition rate, so there won't be like, it won't be in 1:1 ratio. There will be always a different kind of a ratio there. Okay, and let's say, yeah, so the it is inside a vacuum chamber, obviously. So as I have already said, it will be under 10 to the power minus 6 torr. And apart from this, the substrate holder is hold here. It's directly the substrate attached directly on top of this substrate holder, and the vapors are flowing through this. And this crucible, as they have said, it is called a boat in normal condition. And apart from this, yes, so this is the thermal evaporation technique. In most of the sensor fabrication, this is the most easiest, and like it takes very small amount of time. The main time it takes to like have this low pressure, to attain this low pressure. So most of the time is utilized to get this kind of a low pressure. Apart from this, like you won't have the deposition is only for, let's say, if you want a deposition of 200 nanometers, it will only take just, let's say, 20 to 25 minutes maximum. It will take only 20 to 25 minutes. And to attain this kind of a vacuum, it depends on your pump. So there are two types of pumps. The first one is a basic rough pump, or let's say rough vacuum pump. And the second one is a turbomolecular pump. This is TMP. In general, we use it as the TMP, and this one is used as the rough pump only. So we need two types of pumps to get this. So to attain a certain level of vacuum, that may be around 10 to the minus 3 torr. To achieve that, we use the rough pump, and afterwards we use this TMP or turbomolecular pump. So we'll attain this kind of a low pressure, and after that we can deposit this. And at first we'll heat the substrate, and from this substrate, when like there will be a gate on top of this kind of a board, and there will be a gate which will just hold all the vapors inside that, and after a certain time when the deposition rate is a certain amount, we'll just remove the gate and the deposition will be on top of this. So this is the basic principle of thermal evaporation. Apart from this, the one of the most important thermal evaporation technique is sputtering technique, in which the basics idea is same, although we use it in a different way. So we have a cathode material, a bar of a material, let's say, and it's in negative charged. So we usually do it in a environment. In most of the case, it's an argon environment, and in this, so in this case, what happens? There is argon gas is filled inside this chamber. This is the total chamber, and argon gas is filled inside it, and there may be oxygen here as they have shown. But in most of the cases, this is the argon gas, and then what happens that here it is the positively charged gate, right? So these argon molecules here, let's change the color, maybe red. Yeah. So this argon molecules in general just directly moves towards this because it's a positively charged area, as is the negatively charged area. They directly hit the cathode sputtering target here. The cathode sputtering target is heated, and because of that, there are molecules directly coming out of this target, right? So what happens that there is a direct hit from this side to this side, and there will be vacancy of this. So what happens that M molecules will be coming out of this material, and they will get deposit on top of the substrate. This is your substrate, and there will be deposition of this M molecules. And as you can see here that there is oxygen as well. So this M molecules connect with the oxygen to create this MOX. Sorry, let's think. Yeah, so they will be in MOX format. It can be MO2, MO3 like this. So this kind of oxides will be deposited on top of this substrate area, and the byproducts, that is there will be many amount of argons there. There can be few M as well, and the excessive O2. This will just come out of this place. So what's happening? Just I am just repeating myself. So what happens at the first? This is happening in a chamber which is filled with argon gas, right? It may have oxygen or it may not have oxygen. What happens that this is positively charged area and this is a negatively charged area. The argon gas just directly hits on top of this cathode area. There will be cathode ions which come out from this area, and it will get deposited on top of this substrate directly. So the basic difference between this the thermal evaporation with this kind of a sputtering technique is that, as these are like mobile ions, so these are very mobile ions, what will happen, there may be like there may be defects on top of this surface as well, as it directly hits that, but there will be more conformability which we need as well. So if the surface is like this, yes, here you can see as well, na? It is directly out of their line of sight, but still there is deposition on these surfaces as well. So we get more conformability, we get more smoother finish and those things. But what happens, there may be some defects on top of the surface as well. So these are the basic PVD techniques which we use in in every kind of fabrication techniques, the evaporation and the sputtering technique. Apart from this PVD techniques, there are CVD techniques. Like in most of the cases, the CVD techniques are greatly divided into this kind of a things like LPCVD, that is the low pressure CVD, MOCVD, that is the molecular metal organic CVD. There are atmospheric CVD, that is APCVD, and there are low pressure LPCVD as well. And there can be like plasma enhanced CVD where we need a plasma. Yeah, sorry, I missed. I forgot that. So in this case, we need a plasma environment as well. So we need to create a plasma environment. So it is also required of like low pressure along with the high voltage as well. So high voltage is also required along with very low pressure. So due to a change in electric field from this to this, there's a flow of this like atoms there. And we need low pressure obviously because like to give the to increase the the velocity of these particles and also the length the particles can move inside of an like specific pressure as well. And what I was saying that apart from this sputtering and thermal deposition, there are specific techniques of CVD where we use like APCVD, MOCVD, PECVD, this kind of a things. So one of the most important and newer generation thing is ALD. So we'll discuss more about the ALD itself, as it's also another type of like CVD technique. So it is better to understand the newer generation like things. So what happens in ALD? What happens in ALD? There's a basic substrate at first. So basic cleaning is done on top of the substrate. So for the basic cleaning structure, what we do is let's say as like they have. Let's just remove these things. Don't think of these things right now. Yeah. So at first, in the first step, there's a vapor or purge of H2O. So we just purge the vapor of water on top of the substrate to just clean the substrate itself. In the next part, what happens that we'll just purge a basic thing like let's say a hafnium dioxide. So on top of this, there will be few hafnium molecules connected with this. Okay, so this is that. After that, what we do that we give a basic purge of nitrogen gas. So what it will create that there may be also like loosely bound hafnium molecules on top of this or those things. And what will happen after this kind of a purge of this nitrogen gas? So there will be only remaining this bonded hydrogen bonded hafnium oxide or this kind of a particles left, and those this extra things will go away, right? After that, and as you can see, this is only a single atomic layer, right? A single atomic layer on top of this substrate. After that, we can again purge of hafnium dioxide, let's say. So what will happen here? So with this hafnium dioxide, there will be another connection of hafnium dioxide on top of this. So in this case as well, there will be loosely bounded some loosely bounded particles as well. So again, what we do again, we'll just purge nitrogen and we'll just remove the excess thing. So after some time, there will be specifically like if you require like let's say 500 layers, so you can directly just deposit 500 layers, exactly 500 layers. So if you need a specific amount of thickness of your material, you will need a specific amount, let's say if one layer is 1 nanometer, let's say. Okay, so if you need a 20 nanometer one, so you will need exactly that amount of layers on top of your substrate. So this is a very precise way to control your deposition in this case. So at first here you can so let's come to the image as well. So what is done that at first there's a purge of this AlCH3 yeah AlCH3. So what happens that CH4 molecules is a byproduct, and when that is purged, this kind of byproducts is just getting removed, and only this surface is being created, right? After that, there's a water purge. What happens that this kind of a things again comes, and these byproducts are getting removed. So after one by one, there will be layers created, like one atomic layer at a time, but there will be one by one layers. So you can directly make you can make a precise, like if you need a 20 nanometer layer in case of, let's say, PVD kind of a technique. So you may get like 18 nanometer, you may get 19 nanometer. There will be several issues with that, and there won't be any conformity as well. So in this case, as it's a CVD, so there will be conformability as well. It is a very fast process as well, but the major drawback of this process is the high temperature required, because we have to heat the substrates beforehand. So this substrate is already heated. Okay, this is a preheated substrate. This is a preheated substrate. Okay, so we have to preheat the substrate to to obviously, let's say, facilitate this kind of like chemical deposition techniques. So let's go back a bit backwards. So here you can see that I have already added the basic difference among this kind of a techniques with PVD and CVD. The basic difference with ALD is that the growth rate is very low, but you have a precise control of the exact thickness you require, right? The conformability is very high. There will be no issues with the conformability. If you require let's say, a structure like this, it will be like this. If you require a structure like this, the most hard structures are like these structures. So a circular structure or this kind of like rounded shapes are those. So it will be a very conformable as well. So in as I was explaining, like oxide things you normally do with this, nitrides, metals, you can do with that. And apart from this, depending on the temperature like your substrate can handle, you will have to change the temperature as well. Yeah, so this is the self-limiting growth mechanism. So you can just deposit a single atomic layer at a time. So you can just precisely control the thickness you will get after some time. So apart from this, so there are we'll move towards the patterning techniques. The basic patterning technique is a lithography technique, which have based on the different applications and based on the different sources of light, you can just classify. So we'll just learn about the basic lithography technique for now. So a basic lithography technique is divided into eight different parts. So what happens in the first part is that in the first case, the substrate is processed. So what is in a substrate processing? The substrate is it may be preheated a bit. It there may be a coating of let's say, a coating of a adhesive material, which will just enhance the next process step, that is the PR coating or the photoresist spin coating technique. So there on top of silicon wafers, there's a coating technique that is called the OTS coating. So we generally quote OTS to increase the adhesiveness of the PR on top of this kind of substrates that can be silicon or those kind of things. In silicon industry, the OTS is the most used and most utilized liquid. And then afterwards, what we do at first, we need to obviously clean the substrate, but to for the lithography process, this is the main way. So at first we have to clean the substrate for organic contaminants and inorganic contaminants, and based on that, after that we may again also do some kind of a piranha cleaning technique. And after that, we'll just at first step of this lithography, what we'll do, we'll just prepare the substrate for further PR spin coating. After that, the process is spin coating processing, right? So what we'll do, we'll just drop by drop put the PR on top of this substrate. The PR is dropped on the substrate, and then it is spin coated, and there will be a uniform coating of this photoresist. Then the most important part comes in, that is the soft baking. So to just use a PR, you can't use directly a PR. So you have to optimize the soft baking technique as well. To you have to check at how much temperature the soft baking is happening. So you have to heat it a bit, and the PR will get hardened a bit. After that, we'll just put a mask that is called as the photo mask, or you can say the photolithography mask as well. So there will be a light source. Okay, so this is like they have told is as a mold. or it is also called a mask, photolithography mask. Yeah. So then the light source is lined. It can be a UV source as well. So in most of the cases, that is the UV lithography. Then again, there are like some kind of a deep UV lithography where you get a very like miniature kind of a like structure size, and then this like kind of a light is shown on top of this mold or those things, and you will just replicate a specific pattern through this molds, and then there's the development phase where you put the like device structure inside a developer solution, put inside a developer solution, and then the like based on the PR as well, based on the mask as well, several parts of this several parts of this PR structure will get dissolved, and several parts will remain there. Rather, you can say based on the UV exposure on top of the PR, several parts will have chemically bonded and it will get hardened, and several parts won't affect, so they will just remain standing there. So what happens here? So these parts gets dissolved, and the structure is like this. Afterwards, we do a hard baking one. So what is done on the hard baking step is that it is heated, but this time it's like a much higher temperature than the soft baking process. So this structure gets more hardened as well. So after that, what we'll do, this is the most important thing, that is the etching technique. So we'll just etch away. Could you please share every week assignment solutions? Yeah, I'll share that. Yeah. Just let's see. Just wait a second. Yeah. I'll share that. Yeah. So you need any specific solution from any week or those things, or like I'll just explain the solutions as well. But then like for the first few minutes, or let's say an hour, I'll just explain the topics that has been already taught in the class. Yeah. So where was I? So if you have any specific questions, you can ask me, right? And then what happens that we just etch away this layer. It is the blue layer here. So these parts are etched away, and where there is like a protection, this parts gets hardened more and more. So after that, we'll just dissolve the PR away, and this structure will be made on top of your like let's say it can be a organic material, or it can be anything. So this structure of this PR is called the sacrificial layer, because it is anyway sacrificed. It is used to just create this what do I say like this structure kind of a like a specific design, and but it's sacrificed anyway. And apart from this, there's the design on top of your desired material, and you can just directly do this. And this is a very very accurate technique, and you can get a very direct what do I say like design directly on top of your material. So the main thing of this photolithography is that you have to understand more about the photoresist and also the photo mask as well. Okay. So the first thing is this photoresist. So there are two types of photoresist, right? So the first one is a positive resist, and there the second one is a negative resist. Negative resist and the positive resist. So what happens when there's a exposure of light, this parts you can see that this part is getting dissolved, right? So what happens here, that in presence of a positive photoresist, with respect to UV light or those things, this parts chemically reacts and get loosely bounded, right? So when we are just putting this device inside the developer solution, this parts gets dissolved. But in case of like negative PR, what happens that with exposure of light, this part gets hardly binded, and you need UV to just hardly bind this kind of a resist. Like so, this negative resist is used to hardly bind these parts, And what happens that the other part will get dissolved inside of a developer, and these parts will remain there. So there may be specific cases where you want to use a positive PR and a negative PR. Okay, and apart from this, let's we'll just discuss about it a bit. But apart from this, there are two types of masks as well. So there can be a bright field mask and there can be a dark field mask. So what happens in a bright field mask? In a bright field mask, most of the mask is clear, which is made out of it can be made out of a glass or those kind of a things, and the opaque features are created within chrome way. So what happens that in this kind of a thing, you can directly just get a reverse let's say with respect to the mask, the design will be in reverse format. Okay. And apart from this, there can be dark field mask where the most of the mask is opaque, which is made out of a chrome type of material, and the specific designs are in let's say in like normal glass structure. So what happens? It will be in directly copy of the mask. So the design will be directly copy of the mask. So so I guess if you have any question, you can ask me right now. If anyone have any kind of a question, you can directly ask me. Then I'll have some questions regarding this discussions. Then we'll move towards the question and answer session. If anyone have any question, you can directly ask or write in the chat box as well regarding anything up to this. So this can be regarding this photoresist mask types, lithography techniques, then ALD, then sputtering, then thermal evaporation techniques, then deposition, any kind of a things. So or the clean rooms as well.
Sir, I have a question.
Yeah.
This fabrication understood very well, but
Okay.
VLSI also some 45 nm technique, 90 nm
Yeah.
techniques are there. So are they same or similar kind or any different technology?
No. So in most of the cases, what happens that in general use the photolithography technique as well. So
Okay.
here, what happens you can't use a basic photolithography, right? So for a basic structure making on this kind of a thing, you can directly use a normal lithography technique. But in those kind of very precise things, but like 3 nanometer node or this kind of a things, you need a very precise one. So that is an industrial grade lithography techniques where we use like deep UV techniques and those things.
Okay. Okay. Thank
So
you.
that is the same kind of a that works in the same kind of a principle, but
Hmm.
it requires a much costlier machine and costlier materials as well.
Okay. Okay. Sir. Understood.
And
Thank you.
in most of the structures as well. So there's another thing I haven't talked about this, but let's talk about this as well. So there can be a 3D lithography technique as well. So this is a very 2D structure, right? So you need a single material a single design, and you can just make a single design. But in most of the structures, that is not a 2D thing, right? So you can have a simple structure here. On top of that, there may be another structure here. There can be a structure here. There can be a structure here. So you need multiple levels of lithography as well. So you need very precise things. So you can't have a material where the lower level that is already designed is getting dissolved inside a developer, or it's getting distorted with heating or those kind of a things. So this is also a huge concern as well. So there may be in case of sensor fabrication, there may be several steps of lithography as well. So multi steps of lithography is in normal in R&D structure as well, and those kind of a things, it is very much necessary. You may have 13, 14 levels of lithography steps to just create a single device.
This fabrication is only for a single layer, right, sir?
Yeah, this is a basic thing. So this is only a single layer structure, but on top of this let's explain a bit maybe. So if your created structure is like this, on top of this you will just create another layer, but that will be a purely sacrificial layer which will remove afterwards. So there may be a structure. If we need a structure like this, so you will just put a sacrificial layer here, and you will just deposit a layer like this. So So you will just pattern this afterwards, and the layer will look like this. So here there will be something, there will be something, there will be sacrificial layer on top of this. Maybe I'll change the color. So this is your, let's say, sacrificial layer, which will just block these things. And on top of this, there is this new layer, right? This is the new layer. So what afterwards you can remove these structures, and this layer will become like this. So there will be a higher one that is made out of two layers. There will be a single structure like this, there will be a single structure like this. Even like this is also a very complicated process, but this is only a two-step process. So in making a simple sensor, let's say a basic sensor, it requires at least like 12, 11 levels of lithography as well. But this is the basic structure, and the basic principle is same for all the different kind of techniques as well.
Sir, doping is optional, or for every fabrication doping is necessary, sir?
No, like based on your application, it's not like necessary. So, like in most of the cases, in like let's say in R&D sectors, what happens that we in general use a specific kind of a like N plus silicon substrate as well. So it's already pre-doped in pre-doped condition. So if like we require this kind of a thing, we have to dope it, and based on this,
Okay, sir. Thank you, sir.
yeah. Anyone have any other questions? So then I will ask a question regarding this as well. Based on this types of photoresist and types of mask. So let me ask a question then. Okay. So as you can see, with a positive photoresist, we get this is the photo mask, right? So this is your photo mask, and with positive photoresist, we get the exact same pattern. So this is your photo mask, and it is the exact same pattern. That is the direct copy. Okay. With negative photoresist, we get the reverse copy. With bright field mask, we get the reverse copy, and with dark field mask, we get the direct copy, right? So, if we want to create a direct copy, let's say we want to create a direct copy, we'll just take the positive PR with a dark field mask, right? So, is it possible to just create the same thing as already that, like we can take the negative PR with the bright field mask? This is the same thing, right? Because if you are using a negative PR, it is giving you a reverse copy. And while you are using a bright field mask, it will give you a reverse copy as well. So this is kind of the same thing, right? So what do you think? Will it work or not?
It will work, I think, sir.
It will, yeah. So others, anyone have any idea? Anyone have any idea of this? Will it work or not? Let's have another example as well, maybe. So if you are using a positive PR with a bright field mask, you will get a reverse one, right? And similarly, if you are using a negative PR, you are getting a reverse one, and you can use a dark field mask with it. So will it work or not? Both are giving you the same structure, right? Will both the things say, but like remain same or not? And then there may be like some specific cases where you will need to use a positive PR, or you will need to use a negative PR. Maybe you'll need to use a specific dark field mask, or you will need to use a bright field mask. Any ideas like where we can use a specific mask or a specific PR? Anything? You guys can guess, I guess, no? Just guess it. It may be wrong, it may be right, right? So let me answer this question first. Then we'll move towards the questions, and then if you have any queries, then we can discuss it afterwards. So in case of dark field mask, you can see that most of the mask is made out of quartz, right? And the features are only transparent. So it will also change the cost as well, depending on the bright field mask or the dark field mask. So if you have a very fine structure like this, let's say a basic structure like this is only there. So what do you think? Which one will be the costlier one, the dark field one or the bright field one, to make this structure? I'm just talking about the cost itself. Just guess it. Which one will be the costlier, the bright field one or the dark field one? Just to make a simple structure like this. Anyone? So obviously this dark field one will cost you more because you need to just have this amount of glass, and also there will be another issue as well. So if you are shining UV on top of this, there may be issue of shadowing as well. Let's say there may be issues of shadowing here, there may be issues of shadowing here and here. This kind of a thing can happen. But if you are using a totally clear mask with this amount of area, the shape will be very fine. Although there will be another problem that you will have to etch away a very huge portion of thing. So there may be it has to be a very perfect kind of etching where you just need to etch the exact amount and you don't need to over etch or under etch the areas as well. Apart from this, let's say, so in case of positive and negative PR, so in case of the PRs, so there may be an issue with developer as well. If both of the PRs are readily available, if the positive and the negative PR is readily available, there may be issue with the developer as well. So the developer solution, we need to understand the connection with the developer with the PR or the both type of PRs. Apart from that, there may be requirement of a different kind of a light source. Apart from that, there may be issues with cost as well. So these are the basic things for the lithography technique. You need to understand the etching process, and it is not an easy process, obviously. So you have to optimize each and every steps of lithography process. And for multi-level lithography process, as I was already telling you, so what happens in multi-level, there will be multiple levels of optimization as well. Even if you optimize the first layer of the lithography, for optimizing the second layer, you will need to require many more information for that. So you need the information for that level as well, and also to what do I say, to maintain a stable first layer as well. You will need to understand the physics of the first layer and the second layer both at the same time. So you can understand if you are having let's say 11 levels or 12 levels of photolithography technique, so you will need to understand the physics for all the layers. And obviously even if you are etching for 12 times, there may be let's say the structure is like this, okay, and it is divided with 12 structures. Obviously the structures will be different for the structure as well. So what happens that the lower level was etched always, right? For 12 times the lower level will be etched, so it should be stable to hold the whole structure on top of this. So these are the things you need to remember while optimizing a lithography process and these things. So we'll move on to some questions. So let's see what happens. So this is in what do I say? Like in case of atomic force microscopy, so these are like calculation techniques, what you will learn, and also you may have a bit of idea of this kind of a techniques. So there are like three like different things in kind of a these things. Let's say this is your surface, and this is your tip to characterize the surface roughness of your surface to check the roughness of your surface. So there are like three techniques. The first one is the contact based technique where the tip will always contact the surface and there may be fewer scratches and those things. There's another technique that is a non-contact technique. So this will be in very close proximity, but there won't be any kind of a scratches or those things. But based on this it will estimate, right? So there may be some errors as well, and there may be like if let's say there is a pothole, there may be estimation of that incorrectly. And the third one is a different kind of a structure, that is the tapping mode. So what happens in tapping mode, that for an instant it touches the like surface, and for another instant it is just in non-contact mode itself. So by tapping this and with a very faster tapping mode, what happens that it will just realize the roughness of your surface without scratching it too much. Let's say like there will be a bit of scratching, but let's say like without any kind of like hard scratching or those things. So because this kind of a contact mode have issues with like soft materials like organic materials or those kind of things, but this kind of a non-contact mode have drawbacks with like inaccuracy. So there will be issues with inaccuracy, and this kind of a tapping mode is the best way. But obviously there will be like the tips will what do I say, like gets like always it's touching and always it's going upwards, so the tips will lose its sharpness over time. So you'll need to require to change the tips always and every time. So these are the four curves, and what do you think? Which one will be the force? And this distance is defined as the distance to surface with the tip. From this surface to the tip, this is the distance we are talking about, and the force applied on top of the surface. So, what do you think? Which will be the correct one? So, based on like the basic understanding, right? So, when it is touching on the surface, what's happening? It's directly contacted with it. So it's clearly like in non-contact mode, the there's a attractive force working on this. There will be attractive force working on it to like it will pull the tip onto the surface itself. So obviously the non-contact will be inside of this one. So anyways, there's only one answer. That will be the fourth one. And for this case, as you can see, there is no contact, so this is not even repulsive or attractive, so this is not the correct one. In case of non-contact, it is a repulsive, so it can't repulse, right? So as it's an attractive force, the surface will pull the tip towards itself, so it is also wrong, and this one is also wrong. We'll move towards the next question. We have a numerical aperture of a microscope as 1.12, 0.12, sorry, and wavelength of light is 6,000 Armstrong. What is the resolving power of this microscope? Maybe what I'll do, let's do one thing. Maybe I'll just explain the questions and afterwards I'll just move towards the basic discussion parts as well. So numerical aperture is NA, right? That is mu sine theta equals to 0.12, where wavelength lambda is 6,000 into 10 to the power minus 10 meter. That is Armstrong. Resolving power is nothing but 2 times Na divided by lambda, or that is 4 into 10 to the power 5 meter inverse, right? Yeah, meter inverse. So maybe we'll just move to this thing. We'll just ask question directly from this because that's going a bit different. So I have a question here. I guess everyone has understood the basic things of thermal evaporation, right? So we'll just say if, like, let's say there's a case where we need to deposit, let's say gold, okay, and we need to deposit, let's say, 100 nanometers of gold on top of this. On top of, let's say, let's say basic silicon maybe. Okay, so on top of silicon wafer, we need to deposit 100 nanometer of gold, and which will require a 10 to the minus 6 torr of pressure. But if you want to just create a layer of, let's say, like as we know that gold has a very low amount of addition with the surface. So in most of the cases, what we do, we use a chrome gold coating, which may be the chrome may be of like few of nanometers, let's say 10 of nanometers, and the gold will be of 100 of nanometers. So I have a question that if I the required material like on top of my substrate is 100 nanometers of contact. So what do you think? So like we'll just make the chrome of 10 nanometer. We have to make it right. So if we make the chrome of 10 nanometer, will we deposit the gold of 100 nanometer or 90 nanometer? The first question is this. Then I have a follow up question as well. You may write your answers in the chat box. I guess you can just guess it, right? So if it is required of 100 nanometer, There will be obviously a device like a design constraint there. So even if like we require gold of 100 nanometer, we'll still just add a chrome layer of 10 nanometer. So we'll just put the gold of 90 nanometer only. So that was the thing. So we'll move towards the questions again. Yeah. So what is the correct order of this HVAC process? Which one will it be? Let's take, I guess, 1 or 2 minutes, and then I'll come back. And yes, and I'll also require the like the reason. Why do you think so? The first one is obviously preparation of substrate, right? So this is common for each and every cases, right? The first one is substrate preparation. The second step will be metal deposition. We have to deposit the metal, which will just etch afterwards, right? So we'll just deposit the metal. So what will be the next step? So that is the main question, right? We'll just directly etch the metal. We'll just use the photolithography technique. What do you think? So this is the basic substrate which is being prepared. After that, we have deposited metal on top of this metal of like maybe this thickness. What will be the third step? As we have already explained. So at first, what we'll do, we'll just coat with photoresist, right? So a photoresist coat will be done on top of this. So this is the metal we was talking about. This is the basic substrate. On top of that, we'll just put a layer of photoresist. What problem with this is that we can't do photolithography without any kind of photoresist, right? This one is obviously wrong. We can directly it'll etch the metal, right? Because the problem with that is that the total metal will be getting etched, so it is not possible as well. In this case as well, there is issue with the photolithography. The photoresist etching, like the spin coating of photoresist can't come afterwards, right? So the first option is anyways true, but still. So afterwards, what we'll do that sorry, that's a spin coating of PM. After that, we'll just use the photolithography technique and we'll just get a simple pattern. So let's say at first this is the structure. This is your PR, which is already designed, and within the photolithography process itself, there will be structure with this. So this is our metal, and on top of that, after developing, the PR will be removed. So as we can see that the photolithography will do the photolithography. Afterwards, we'll just develop the solution. So in case of development, what will happen? That will just dissolve these portions. So like this portions will get dissolved afterwards. Then we can etch the substrate and we can just metal it, right? We can etch the metal, sorry, not the substrate, we can etch the metal and we'll just have a simple structure afterwards. This is our substrate. On top of that, there will be metal structure, and we'll just remove the excess photoresist from our devices. So this is the follow technique. So the option one is the correct one. Then we'll move to the next question. Which one is true for the E-beam lithography techniques? Light is required for E-beam. Mask process is required. Feature size is large in E-beam, or exposure that is done in sequences is required in E-beam. So in case of E-beam lithography technique, if we are using the lithography technique with E-beam, that is called as the E-beam lithography. Light source is the light source is E-beam, right? So what is required? Anyways, like as directly we can see, right? The first thing we require is the sequential exposure of E-beam. That is the main answer. So this is the sequential exposure of that occurs in E-beam. We'll move towards the next question. Which one is the true one, like regarding the etching process? Selectivity should be very low. Etch rate for thin film should be very low. Etch rate for mask should be high. Undercutting is seen mostly in wet etch. So the answer for this is etch rate for the mask should be high. What do you think? Is obviously not, right? If the mask is getting etched at the first, so it will be a very huge issue, right? So it is not. Etch rate for the thin film should be very low. It is not as well because, like in both the cases, let's say if our structure is like this and our mask is like this, right? If the mask is getting etched very fast, what will happen? There will be only a single dip here. That will be the structure afterwards, and we'll just remove these parts, and this will be the structure. If in similar case the like thin film structure is very low, what will happen? Like in the similar case of this, there will be a simple dip in this. There will be this like here there will be the mask, although still there will be a single dip. So we need we need just the opposite, right? We need the etch rate of the film to be very high, although we need the etch rate of the mask to be very low. Okay. Selectivity should be very high. If you want to etch a certain area, let's say like you have a structure like this and you have to etch this area. This is from a top view, let's say, and you have to etch this area. So you have to be like able to just etch that directly that area only, because selectivity has to be very high anyways. you have to select a certain area to be etched at first, and then you can etch the other areas afterwards. So it is obviously wrong. The last one is right because undercutting is mostly seen in the wet kind of etch, where we etch with a liquid. So there's a issue with that undercutting. Yeah. So this is the question where the etching process is seen that the vertical length of the etch is 100 nanometer, 100 micrometers, and undercutting length is 40 micrometers. We need to determine the value of anisotropy in the etching process. So let's do this. Here, what happens that anisotropy in the etching process is equals to vertical length of the etch divided by the undercut length. Okay, so we'll just divide this by this. So the vertical length is given is 100 microns, but the undercut length is nothing but 40 microns. So it is nothing but 2.5. So the 2.5 will be the correct answer. Now, the next question is the maximum concentration for thermal diffusion and ion implantation is respectively at where? Surface, below the surface, surface, below the surface, below the surface, and both at the surface itself. So the correct answer is surface and below the surface. And why is it? Because the maximum concentration of thermal diffusion happens at the surface. Okay, because this is a diffusion kind of a technique, so the diffusion will move downwards from the surface itself. While in case of like ion implantation techniques, the diffusion, sorry, in case of like ion, what do I say, like ion implantation, the ion penetration of the material, like the ion penetration of the material will come from like below the surface. So from below the surface. Okay, so the first one will be the correct one. Let's move to the next question. What is the wavelength of an optical microscope and electron microscope? So the for the wavelength of the optical microscope is 600 nanometers, where the electronic microscope can go towards this 0.012 nanometers. That's why we require a like electrical microscope anyways. The next one is question number 9. The arrangement of components in scanning electron microscope is from top to bottom. At first, in case of like scanning electron microscope, there will be the E-gun, that is the source of electron. Then there will be an anode chamber which will just accelerate the electrons. There will be a condenser lens which will condense the electron beam. There will be an objective lens which will just direct the electron beam to a certain space. There will be the backscatter detector that will detect the scattered electrons. There will be an X-ray detector which will detect the X-rays, and there will be the sample holder. So there will be a sample, and then the scattered electrons will be detected through that, and then there will be a X-ray detector which will be afterwards. And so today's last question is this one. the correct order of lateral resolution. So which one have the higher resolution in this case, right? So obviously AFM will have the higher resolution in case of like lateral cases. So AFM will have the higher resolution. After that, SIM will have the second high resolution. It is the scanning electron microscope. Afterwards, TIM will have the third highest resolution. And finally, STM, that is the scanning tunneling microscope. It will have the lastly the lowest resolution among these things, right? So we'll just conclude today's session and we'll meet on the next Monday.